Tonight, we embark upon an extraordinary journey, a vast, sweeping narrative that stretches across the immense canvas of cosmic time, from the very genesis of everything we know to the distant, inevitable twilight of our home. This is the story of Earth, not just its brief, vibrant life, but its origins, its evolution, and its ultimate fate, all woven into the grander chronicle of the universe itself. We will drift through eons, observing the silent, profound transformations that have sculpted galaxies, birthed stars, and eventually given rise to the intricate dance of life on this singular blue planet. Our exploration will be a calm, measured contemplation, inviting you to simply listen and allow the sheer scale of existence to unfold around you. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our journey through the history of our planet, this shimmering, living orb we call home, begins long before the formation of the Earth itself, even before the very conception of our familiar solar system. We must cast our minds back, far beyond the familiar cycles of seasons, beyond the ancient whispers of the first life forms, into an era of almost unimaginable antiquity. This story, in its truest, most foundational sense, commences in the fathomless immensity of space, at a time when the universe as we perceive it, with its galaxies, its stars, its fundamental laws, was poised on the precipice of its very birth. It was a moment of profound cosmic anticipation, a silent genesis, a profound stillness before the eruption of all existence. The most widely embraced scientific framework for understanding the universe's origin, a profound and elegant theory, is known as the Big Bang. This isn't just a hypothesis, it's a meticulously constructed narrative built upon a mountain of observational evidence and theoretical physics that describes an event marking the inception of absolutely everything. It was the primordial instant, when time itself began its relentless march, when the very fabric of space unfurled, when matter coalesced from pure energy, and when the fundamental forces that govern the cosmos first took their distinct forms. Imagine, if you can, a moment, roughly 13.8 billion years ago, when the entire observable universe was not spread out across billions of light years as it is today, but rather was compressed into a state of unimaginable concentration. This primordial state is often referred to as a singularity. It wasn't a point in space, for space itself had not yet expanded into being, but rather a state of infinite density and temperature. In this utterly extreme environment, the very principles of physics that we rely on to understand the cosmos, the laws of gravity, electromagnetism, and the strong and weak nuclear forces, simply do not apply. Our current understanding of reality, our mathematical models, our very intuition about how things work, completely breaks down at this boundary. The concept of time, usually so linear and absolute, becomes incredibly nebulous, almost meaningless, in such an unfathomable condition. It's a realm beyond our direct experience, a true cosmic enigma. From this enigmatic singularity, the universe began its monumental transformation, embarking on an explosive event that we've come to call the Big Bang. It's crucial to understand that this was not an explosion in the traditional sense, not like a firework detonating in a pre-existing void, scattering fragments outwards. Instead, it was a sudden, incredibly rapid, and accelerated expansion of space itself. The space between everything began to stretch, to swell, carrying matter and energy along with it. Think of it less as something exploding eyes into space, and more as space itself inflating from an incredibly tiny, super dense speck into something unimaginably vast in a fleeting instant. In those earliest, most incandescent moments, the universe was a place of astonishing extremes. It was incredibly, unimaginably hot, a searing inferno of pure energy, far hotter than the core of any star we know. And it was incredibly dense, packed with the nascent ingredients of all future matter. As this nascent cosmos expanded with breathtaking speed, it began a process of gradual, yet rapid, cooling. This cooling was the crucial prerequisite, the essential condition that allowed the fundamental particles of matter, the very building blocks of everything, to begin their formation. It was a delicate balance: too hot, and particles couldn't coalesce; too cold, and the energy wouldn't be sufficient for their creation. And so, from this swirling, energetic plasma, the very first, most elemental components of the universe began to emerge. These were the quarks, tiny, enigmatic particles that are never found in isolation, and the electrons, those incredibly light, negatively charged particles that orbit the nuclei of atoms. They were ephemeral, flickering into and out of existence in the superheated environment, but their presence marked the true beginning of baryonic matter, the stuff that makes up stars, planets, and ourselves. It was a truly foundational moment, the first steps from pure energy to concrete physical reality. For the initial few minutes following this cosmic genesis, the universe continued its relentless expansion, and with that expansion, its temperature continued to drop. This cooling was vital, allowing the quarks, those fundamental constituents, to combine and form more stable, composite particles. These were the protons and neutrons, the heavier, positively charged and neutral particles that would eventually form the nuclei of atoms. Imagine this primordial soup, a churning, chaotic mix, where these nascent particles were constantly forming and reforming. As the universe cooled further, these newly formed protons and neutrons began to interact in a process known as primordial nucleosynthesis. This was the universe's very first foray into alchemy, a cosmic forge creating the lightest elements. Through a series of nuclear fusion reactions, protons and neutrons fused together, creating the first atomic nuclei. At this nascent stage, the universe primarily manufactured the lightest elements, hydrogen and helium. These two elements, hydrogen with its single proton, and helium with its two protons and usually two neutrons, would go on to constitute the vast majority of the baryonic matter in the universe. Even today, billions of years later, these two simple elements dominate the cosmic landscape, forming the fuel for stars and the raw material for future stellar alchemy. During this early, incredibly dense and hot phase, light itself was trapped. It couldn't travel freely through the universe. The cosmos was an opaque, murky fog, a plasma where electrons were not yet bound to atomic nuclei. Photons, the particles of light, were constantly scattering off free electrons, unable to escape the dense, ionized environment. It was a universe without transparency, a realm where light was born but could not yet shine freely across vast distances. However, as the cosmic clock ticked forward, approximately 380,000 years after the Big Bang, a pivotal transformation occurred. The universe had continued its inexorable expansion, cooling to a critical temperature. This cooling finally allowed the free electrons and the atomic nuclei, primarily hydrogen and helium nuclei, to combine and form stable, neutral atoms. This momentous process is known as recombination. It was a cosmic turning point. With electrons now bound to nuclei, the universe suddenly became transparent to light. The photons, previously trapped, were finally released, free to travel unimpeded through the newly clarified expanse of space. The ancient radiation resulting from this very moment, this cosmic unbinding of light, is still detectable today. It's what we call the cosmic microwave background radiation, often abbreviated as CMB. This faint, pervasive glow, bathing the entire universe, is a crucial relic, an invaluable echo from the early cosmos. It's a direct glimpse, a fossilized photograph, if you will, of the universe as it was nearly 13.8 billion years ago, offering scientists profound insights into its initial conditions, its composition, and its subsequent evolution. It's a testament to the enduring power of these ancient events, still whispering across the vastness of time. As millions upon millions of years continued to unfold, the universe persisted in its grand, silent expansion, and its overall temperature continued its gradual descent. But within this outwardly uniform expansion, subtle, almost imperceptible variations were at play. Quantum fluctuations, tiny, random deviations in the density of matter and energy that existed in the very early universe, began to exert their influence. These minute irregularities, though initially minuscule, served as the essential seeds, the gravitational nuclei, for the large-scale structure that we observe so strikingly today. Under the inexorable, long-range influence of gravity, matter, ever so slowly, began to clump together. These slightly denser regions, drawing in more and more surrounding material, started to condense into the first massive gas clouds. Imagine these embryonic structures, diffuse and vast, composed almost entirely of the primordial hydrogen and a smaller, yet significant, amount of helium, the elements forged in the furnace of primordial nucleosynthesis. These majestic, swirling clouds, stretching across truly immense cosmic distances, were not merely random aggregations. They were the nurseries, the fertile grounds, where the first generations of stars would eventually be born. The formation of these first stars, glistening points of light in an otherwise dark and expanding universe, marks an absolutely crucial stage in the intricate tapestry of cosmic evolution. Within the heart of these gigantic cosmic forges, these colossal nebulae of gas and dust, the relentless pull of gravity continued its work. As the gas clouds collapsed further under their own immense weight, the pressure and temperature at their cores increased to unfathomable levels. Eventually, these conditions became so extreme, so incandescent, that they were sufficient to ignite nuclear fusion. Nuclear fusion, the very process that fuels stars throughout their luminous lives, is a truly alchemical transformation. It's where lighter atomic nuclei, primarily hydrogen, are forced together under immense pressure and heat, fusing to form heavier elements, such as helium, releasing an enormous amount of energy in the process. This outpouring of energy is what makes stars shine, radiating light and heat across the vast interstellar voids. The first generations of stars, born from these pristine, hydrogen-rich clouds, were often truly massive, incandescent giants. They burned through their nuclear fuel at an astonishing rate, living lives that were incredibly short by cosmic standards, perhaps only a few million years, compared to our sun's projected lifespan of billions. Yet, their brief, brilliant existence was utterly crucial to the chemical evolution of the universe. At the dramatic end of their lives, these colossal, first-generation stars met their demise in spectacular fashion. They exploded as supernovae. These cataclysmic events, among the most energetic phenomena in the universe, are not merely stellar deaths, they are cosmic rebirths. The explosions scattered the newly forged heavy elements, created in the star's cores through further fusion processes throughout the vast interstellar medium. Elements like carbon, oxygen, iron, and countless others, essential for the formation of planets and life, were flung out into the galactic nurseries. These supernova remnants, these clouds enriched with a fresh infusion of heavier elements, then became the raw material for the next generations of stars. This enrichment was a profound game changer. It meant that these subsequent gas clouds possessed enough chemical diversity, enough of these newly synthesized heavy elements, to allow for the formation of not just stars, but also planetary systems. And crucially, within these systems, there was now the potential for the formation of rocky planets, worlds like our Earth, capable of harboring the complex chemistry necessary for life. Within these bustling star-forming regions, these magnificent nebulae, it wasn't just individual stars that were being born. Entire galaxies, colossal collections of billions upon billions of stars, along with vast reservoirs of gas, dust, and the mysterious dark matter also began to take shape. Gravity, acting on these enormous scales, drew these nascent stellar nurseries together, sculpting them into the majestic, spiraling, or elliptical forms we observe across the cosmos today. These early galaxies, slowly but surely, began to coalesce, creating the enormous and incredibly complex network of cosmic structures that now permeates the universe. So, from that initial, infinitesimal point of the singularity, through the tumultuous birth of the first particles and elements, to the glorious formation of stars, and then, finally, the grand, sweeping architectures of galaxies, the universe has been in a state of continuous, dynamic evolution. This initial, breathtaking chapter of cosmic history lays the fundamental groundwork, the essential precursor, for understanding not only our own minuscule place within this boundless expanse, but also the very origin of all the fundamental elements that constitute our planet, and indeed, the intricate miracle of life itself. It is a story of profound beginnings, of transformations on scales that humble the imagination, and of the fundamental forces that continue to shape everything around us. Now, as the cosmic dust begins to settle, and the first galaxies coalesce into glittering islands of light across the expanding dark, we turn our attention to a more localized, yet equally profound, narrative. Having witnessed the grandiose display of the Big Bang and the subsequent formation of the first stars and galaxies, the cosmic stage was meticulously set for the next, equally compelling act, the formation of our very own solar system, and with it, the birth of the Earth. This chapter, then, will delve into the extraordinary, often violent, and immensely intricate story of how our blue planet was forged from the swirling remnants of cosmic dust and gas approximately 4.5 billion years ago. The dramatic stage for Earth's formation was not set in a pristine, untouched corner of the universe. Rather, it was prepared by a previous stellar drama, the cataclysmic death of an ancient star, perhaps one of those massive, short-lived first-generation suns we just discussed. Its spectacular supernova explosion, a final, brilliant act of stellar defiance, scattered a rich bounty of heavy elements into the vast, cold expanse of interstellar space. These precious elements, forged in the heart of that long, dead star, and then flung outwards, mingled with the predominant hydrogen and helium that had originated in the Big Bang. This mixture slowly, silently, began to form a dense molecular cloud, a colossal, dark nebula, which would become the primordial material, the cosmic clay, from which our entire solar system would eventually emerge. Within the silent, swirling depths of this massive cloud, often referred to as the solar nebula, a disturbance occurred. The precise trigger for this disruption remains a subject of scientific inquiry, but a leading hypothesis suggests it was possibly caused by the shock wave generated by a nearby supernova. Another stellar death, echoing through the cosmos. This ripple of energy, this cosmic impact, caused a section of the nebula to become gravitationally unstable. Under its own immense gravity, this portion of the cloud began an inevitable, slow, yet powerful collapse. As this vast nebula contracted, pulling its diffuse material inward, a fundamental physical principle came into play: conservation of angular momentum. Just as a spinning ice skater draws their arms inward to spin faster, the collapsing cloud began to rotate with increasing speed. This rotation, combined with the inward pull of gravity, caused the cloud to flatten into a vast, swirling, rotating protoplanetary disk. At the very center of this rapidly spinning disk, the densest material accumulated, heating up to incandescent temperatures, eventually forming a hot, glowing central core, the embryonic sun, our future star. The rest of the disk, a swirling platter of gas and dust, would be the birthplace of the planets. Within this dynamic, swirling protoplanetary disk, the processes of planetary formation truly began. Materials, initially fine dust particles and gas, started to clump together through a process known as accretion. Imagine microscopic grains of cosmic dust, bumping into each other, gently sticking together due to electrostatic forces, like dust bunnies forming under a bed, but on a cosmic scale. Over vast stretches of time, these tiny clumps grew larger and larger, gradually forming pebble-sized aggregates, then meter-sized boulders. These larger clumps, in turn, continued to collide and merge, slowly but surely forming planetesimals, solid bodies, many kilometers in diameter, roughly the size of asteroids. These planetesimals, now substantial enough to exert their own gravitational influence, began a more violent and accelerated phase of growth. They kept colliding and merging, gravitationally attracting one another like cosmic billiards on an unimaginable scale. Each collision, each merger, added mass to the growing bodies, forming larger and larger protoplanets. These embryonic worlds, still far from their final form, carved out paths within the protoplanetary disk, sweeping up remaining debris as they orbited the nascent sun. Our Earth, the very world beneath our feet, formed within a specific region of this bustling disk, often referred to as the habitable zone. This was the sweet spot, the region where temperatures were just right, neither too hot nor too cold, to allow for the eventual existence of liquid water on its surface. This seemingly subtle distinction would prove to be absolutely critical for the future development of life. As the Earth grew, relentlessly accumulating material, its gravitational pull became stronger and stronger, attracting more and more of the surrounding planetesimals and debris. This process dramatically increased its mass and, consequently, its density. This early period of Earth's growth was an incredibly violent epoch, characterized by constant, colossal collisions and mergers, shaping and reshaping the young planet with each impact. One of the most profoundly significant collisions in Earth's tumultuous early history involved a colossal impactor, a Mars-sized protoplanet, often referred to by the evocative name Theia. This was not a glancing blow, but a truly colossal, planet-altering crash. This immense impact, occurring perhaps 4.5 billion years ago, not only had far-reaching implications for Earth's future climate and the succession of seasons by drastically altering the tilt of our planet's axis, but it also ejected an absolutely enormous amount of molten rock and debris into orbit around the Earth. This incandescent ring of material, a fiery halo surrounding the young Earth, would eventually coalesce to form our steadfast companion, the Moon. Meanwhile, within the Earth itself, a process of profound internal restructuring was underway. As the planet continued to heat up from the immense energy of accreting impacts and the decay of radioactive elements, its interior became molten. Heavier elements, such as iron and nickel, began their slow, inexorable descent toward the center of the planet, drawn by the immense gravitational forces. This process, known as differentiation, resulted in the formation of Earth's dense, metallic core. Concurrently, lighter materials, such as silicates, rose toward the surface, forming the planet's mantle and eventually its nascent crust. This internal differentiation was absolutely crucial, for it was the movement of this molten iron core, churning and flowing, that would eventually establish Earth's powerful magnetic field. This invisible shield plays an utterly vital role even today, protecting our delicate planet from the relentless onslaught of harmful solar wind and cosmic radiation, making the surface a far safer place for life to develop. Earth's very first atmosphere, a primordial veil, formed primarily from the gases released through intense volcanic activity. These early volcanic emissions included vast quantities of water vapor, along with significant amounts of carbon dioxide, ammonia, and methane. However, this initial, nascent atmosphere was strikingly different from the one we breathe today. It conspicuously lacked free oxygen. It was a suffocating, anoxic environment, utterly inhospitable to most modern life forms. over immense stretches of time, and through a complex interplay of geological processes and, crucially, the emergence of early biological activity, the Earth's atmosphere and its overall chemical composition would continue their slow, dramatic evolution, gradually transforming into the oxygen-rich, life-sustaining environment that we recognize and depend upon today. This planetary metamorphosis was a silent, protracted drama, played out across billions of years. Now, let us turn our gaze to that luminous celestial body that graces our night sky, the moon. That silver beacon, illuminating our darkest hours, is far more than a simple aesthetic decoration in the vast cosmic tapestry. Its very existence is intrinsically, profoundly linked to the history of the Earth itself, playing an utterly crucial and multifaceted role in the intricate evolution of our planet. The moon has been a silent witness, a constant companion, influencing Earth in ways both subtle and profound since its violent genesis. The genesis of the moon is a story of cosmic cataclysm, a dramatic, singular event that not only gave rise to our planet's only natural satellite, but also fundamentally shaped the future course of Earth's geological, climatic, and biological evolution. It was a moment of immense violence and creation, a testament to the chaotic beauty of the early solar system. The most widely accepted and scientifically robust theory explaining the moon's formation is known as the giant impact hypothesis. According to this compelling theory, approximately 4.5 billion years ago, in the tumultuous period shortly after Earth's initial formation and differentiation, a colossal body, often referred to as Tia, a protoplanet roughly the size of Mars, collided with our nascent planet. This was no gentle embrace, no mere glancing blow. It was an absolutely catastrophic, head-on crash, an impact of such immense energy that it irrevocably altered the fate of both celestial bodies. The sheer violence of this impact was enough to melt and vaporize a significant portion of Earth's outer layers, tearing away vast quantities of its mantle and crust. Simultaneously, Tia itself was largely disintegrated, its constituent materials vaporized and flung outwards. This immense amount of superheated, molten rock and metal vapor, ejected with incredible force, formed a vast, incandescent ring of debris that began to orbit our planet. Held in place by Earth's powerful gravitational embrace, this fiery halo slowly, majestically, swirled around the young Earth. Imagine a ring of fire and glowing dust, constantly colliding and interacting, eventually spanning thousands upon thousands of kilometers. In the aftermath of this truly titanic impact, the swirling debris within this orbiting ring began a process of gradual coalescence, drawn together by its own collective gravity. This accretion process, remarkably similar to the mechanism that formed Earth and the other celestial bodies in the first place, slowly but surely gave rise to the moon. The molten materials and vaporized rock within the debris disk merged, solidified, and gravitationally drew together, forming a new, substantial celestial body. This incredible process, from violent ejection to the formation of a coherent satellite, may have taken a surprisingly short amount of time in cosmic terms, perhaps only a few hundred years. The formation of the moon from this chaotic, incandescent aftermath had truly profound and far-reaching implications for both the newly formed satellite and its parent planet. The young moon, immediately after its birth, was not the cratered, serene body we see today. Instead, it was an incredibly hot, glowing sphere, a world entirely covered by a deep ocean of molten rock. Over vast spans of time, this primordial magma ocean slowly cooled and solidified, eventually forming the thick, ancient lunar crust that we can still observe, albeit scarred by billions of years of impacts. This cataclysmic event also had an immense and lasting impact on Earth. The collision drastically altered the tilt of Earth's rotational axis, setting it at an angle of approximately 23.5 degrees relative to its orbital plane around the Sun. This axial tilt is directly responsible for the beautiful and predictable succession of seasons that we experience today, a fundamental driver of Earth's climate and ecosystems. Furthermore, the very presence of the Moon, with its substantial gravitational pull, is believed to have played a critical role in stabilizing Earth's axial tilt over geological eras. Without the Moon's steadying influence, Earth's tilt might have wobbled far more dramatically, leading to much more extreme and unpredictable climatic shifts, which would have presented significant challenges for the long-term evolution and stability of life. The formation of the Moon also had less obvious, yet equally significant, implications for the internal dynamics of the Earth. The colossal impact could have contributed to a profound reorganization of Earth's already differentiating core and mantle, influencing the convection currents within the mantle and potentially affecting the strength and stability of Earth's magnetic field, that vital protective shield. Additionally, the energetic formation of the Moon may have influenced the early evolution of Earth's atmosphere, perhaps by contributing to the removal of some volatile gases from our planet's nascent envelope, altering its initial composition. Over the eons, the intricate and dynamic relationship between Earth and its silent companion, the Moon, has continued to evolve and deepen. The Moon's powerful gravitational pull is directly responsible for the rhythmic ebb and flow of tides in Earth's vast oceans. These tidal forces, far from being a mere curiosity, have been a crucial factor throughout Earth's history, profoundly influencing the evolution of marine life and shaping countless ecological cycles along coastlines. It is even hypothesized that the rhythmic action of the tides, exposing and re-exposing tidal pools to the air and sun, may have played a critical, perhaps even indispensable, role in facilitating the monumental transition of early life forms from their aquatic cradles to the challenging, yet ultimately rewarding, terrestrial environment. The Moon, our constant companion, has silently witnessed the entire unfolding drama of Earth's history. From the tumultuous, fiery birth of our planet to the quiet proliferation of life across its surface, the Moon has been an unwavering observer. Its heavily cratered surface, a pockmarked testament to billions of years of cosmic bombardment, tells a vivid story of a dynamic and often violent cosmos, replete with impacts and collisions that have shaped our solar system. Lunar exploration, through both robotic probes and human missions, has provided scientists with an invaluable treasure trove of information about the early history of Earth and the entire solar system. The rocks and regolith brought back from the Moon offer tangible clues, chemical fingerprints, to the ancient processes that sculpted our world and laid the foundation for the unique conditions that allowed life to flourish. Now, as our gaze shifts from the fiery birth of the Moon and the early, violent shaping of Earth, we delve into another absolutely fundamental chapter in our planet's saga: the Age of the Oceans. The history of our planet is an intricate narrative, profoundly and inextricably intertwined with the development, the deepening, and the ceaseless evolution of its vast, shimmering oceans. These colossal bodies of water are far more than mere geographical features, more than just blue expanses on a map. They are, in a very real and profound sense, crucial to the very existence of life as we know it, acting as both cradle and crucible for biological complexity. The formation of Earth's oceans, those vast reservoirs of life-giving liquid, began approximately 4.4 to 4 billion years ago. This was a period when the planet's surface, having cooled sufficiently after its initial formation and the giant impact that created the Moon, finally reached temperatures low enough for liquid water to stabilize. Before this, any water would have instantly vaporized in the searing heat of the early Earth. Water, that indispensable, vital resource, reached Earth through a variety of cosmic delivery mechanisms. One significant source is believed to have been the relentless bombardment of ice, rich comets, and asteroids that impacted the planet during its tumultuous youth. These icy visitors, crashing into the young Earth, delivered vast quantities of water, gradually accumulating in basins and depressions. Additionally, a substantial amount of water was also released from within the planet's interior itself, through a process known as volcanic degassing. As Earth's molten interior churned and volcanoes erupted with furious intensity, vast plumes of water vapor and other gases escaped from the molten magma, rising into the nascent atmosphere. As this atmospheric water vapor cooled, it condensed and precipitated as incessant, torrential rain, a deluge that lasted for millions of years, slowly but surely filling the emerging ocean basins and sculpting the nascent continents. As these vast, primordial oceans formed and deepened, they immediately began to provide a stable, relatively protected environment. A perfect laboratory, if you will, for the complex chemistry of life to begin its earliest, most tentative experiments. The oceans, with their immense thermal capacity, not only played a crucial role in moderating Earth's volatile climate by absorbing and redistributing solar heat across the globe, but they also served as the warm, nutrient-rich cradles for the earliest forms of life. In this primitive soupy broth, a rich concoction of inorganic and organic molecules, bathed in energy from volcanic vents and solar radiation, had the unprecedented opportunity to interact, to react, and eventually to self-organize, forming the first simple, rudimentary biological structures. The profound importance of water for life, in all its myriad forms, is multifaceted and utterly fundamental. Firstly, water is an exceptional solvent. This means that a vast array of substances, salts, minerals, organic compounds, can readily dissolve within it, creating a dynamic medium where countless chemical reactions, absolutely necessary for the processes of life, can easily occur. Without this solvent property, the complex metabolic pathways within cells would be impossible. Secondly, water possesses an extraordinarily high heat capacity. This remarkable property allows the oceans to absorb and store immense amounts of heat energy from the sun, slowly releasing it, thereby stabilizing Earth's global climate and preventing extreme temperature fluctuations that would be devastating for delicate biological systems. Imagine a world without this thermal buffer, with daily temperature swings of hundreds of degrees. Life as we know it could never have taken hold. Additionally, water is intrinsically crucial for cellular metabolism, acting as a direct participant in countless biochemical reactions, and it serves as the primary transport medium for nutrients, gases, and waste products both within individual organisms and throughout entire ecosystems. Earth's oceans, then, were not merely passive backdrops, they were the dynamic, living stage upon which some of the most significant milestones in the entire history of life unfolded. It was within these ancient, saline depths that the very first known forms of life arose, microscopic entities that began the unbroken chain of evolution stretching to every living thing on Earth today. Throughout immense geological eras, the oceans have been both silent witnesses and active, shaping participants in the ceaseless drama of life's evolution. From the simplest, single-celled microorganisms that first emerged billions of years ago, to the breathtakingly complex and diverse marine ecosystems we marvel at today, the oceans have fostered an astonishing array of biological innovation. They have endured countless mass extinctions, rebounded with renewed vigor, and remained home to an astonishing diversity of life, from the vibrant, kaleidoscopic coral reefs teeming with color, to the mysterious, crushing depths inhabited by bizarre creatures that seem to have emerged directly from the pages of science fiction, adapted to conditions of extreme pressure and perpetual darkness. Now, we shift our focus to the truly miraculous, the very genesis of life itself, a story of incredible resilience and profound adaptation, the dawn of life. The tale of life on Earth is not one of sudden appearance, but a slow, persistent narrative of resistance against formidable odds and an astonishing capacity for adaptation, beginning with the humblest, most unassuming of protagonists, microorganisms. The dawn of life, a period that stretches back more than 3.5 billion years into the planet's deep past, marks the seminal beginning of this evolutionary journey, a journey that first stirred and took its earliest, tentative forms deep within the protective embrace of the oceans of early Earth. The earliest, most ancient signs of life, whispered from the geological record, are found embedded within ancient rock formations. Here, scientists have uncovered microscopic structures, often laminated and dome-shaped, known as stromatolites. These stromatolites offer compelling fossil evidence of primordial microbial communities. These remarkable structures, formed by successive layers of microorganisms, primarily cyanobacteria, and the sediments they trapped and bound together, are truly stony witnesses to the early, persistent presence of life on our planet. The careful dating of these incredibly ancient fossils strongly suggests that life has been an active, transforming force on Earth for at least 3.5 billion years, and tantalizing evidence even hints that it may have emerged even earlier, pushing the boundaries of what we thought possible. These earliest inhabitants of Earth were primarily prokaryotes. These are simple, single-celled organisms, distinguished by their lack of a defined, membrane-bound cell nucleus and other complex organelles. They were the trailblazers, the pioneers of the biological world. Among these early, ubiquitous prokaryotes, a particular group, the cyanobacteria, played an absolutely crucial, planet-altering role in the transformation of Earth's very atmosphere and, consequently, its future trajectory. These remarkable photosynthetic organisms possessed the revolutionary ability to harness the energy of sunlight and convert carbon dioxide from the atmosphere into their own energy, and, critically, oxygen as a byproduct. This gradual, relentless release of oxygen into a previously anoxic atmosphere was not a minor event. It was a planetary-scale transformation, an environmental revolution known as the Great Oxidation Event, or sometimes the oxygen catastrophe, depending on one's perspective. This monumental event was a turning point, a pivotal moment in Earth's history, fundamentally altering the composition of the atmosphere over hundreds of millions of years. It gradually created an oxygen-rich environment, a completely new atmospheric chemistry, which would eventually allow for the evolution of far more complex life forms, paving the way for everything that would follow. For many existing anaerobic life forms, this was indeed a catastrophe, but for the trajectory of complex life, it was the dawn of a new era. The initial evolution of microbial life, though incredibly slow by human standards, was persistent and steady. These early, tenacious organisms demonstrated an astonishing capacity to adapt to an incredibly wide range of extreme environmental conditions across the nascent planet. Microorganisms showcased an amazing, almost unparalleled ability to inhabit and thrive in virtually every conceivable corner of the planet. From the scorching, superheated waters of volcanic hot springs to the frozen, crushing depths of the deepest oceans, passing through highly acidic and intensely alkaline environments, these tiny life forms demonstrated a versatility and resilience that is truly breathtaking. This incredible diversity of habitats, colonized and exploited by microbial life, profoundly reflects their inherent adaptability, their fundamental robustness, and their sheer tenacity. Characteristics that have been absolutely fundamental for their continued survival, their diversification, and their ongoing evolution throughout billions of years. Microbial life, in its silent, persistent activity, not only adapted the planet for the future emergence of more complex forms of life, but also laid the foundational biological and biochemical groundwork for the subsequent evolution of biological complexity itself. Through intricate processes such as symbiosis, where different organisms live in close association for mutual benefit, and horizontal gene transfer, where genetic material is passed between organisms not through reproduction but directly, microorganisms developed an astounding array of new metabolic pathways and physiological capabilities. These ingenious biological innovations, these incremental steps in cellular machinery, would prove to be absolutely crucial for the eventual development of eukaryotic life. Eukaryotic organisms are characterized by their more complex cells, possessing a defined nucleus that houses their genetic material and other membrane-bound organelles. These are the organisms that, over immense spans of time, would give rise to the majestic plants, the diverse animals, and the ubiquitous fungi that populate our world today. One of the most profoundly significant events in the early, foundational evolution of life, a true cellular revolution, was the appearance of the eukaryotic cell. This monumental evolutionary step, a leap in cellular complexity, is understood to have involved a process called endosymbiosis. This theory posits that certain types of free, living bacteria were incorporated into larger, host cells, forming a symbiotic relationship where both benefited. Over vast stretches of evolutionary time, these incorporated bacteria lost their independent existence and became specialized organelles within the host cell. For example, mitochondria, the powerhouses of eukaryotic cells responsible for energy production, are believed to have originated from aerobic bacteria, while chloroplasts, the sites of photosynthesis in plant cells, are thought to have evolved from photosynthetic cyanobacteria. This endosymbiotic event was absolutely essential for the development of greater cellular complexity, allowing for vastly increased energy efficiency and a degree of cellular specialization previously unattainable. This breakthrough fundamentally paved the way for the remarkable diversification of multicellular life, enabling cells to work together in highly organized and specialized ways. The transition from single-celled existence to the intricate, cooperative world of multicellular life was another monumental milestone in the long, unfolding history of biology. The very first multicellular life forms, rudimentary aggregations of cells working in concert, appeared approximately 1,000 to 600 million years ago. This groundbreaking shift, from solitary existence to coordinated cellular communities, was the essential precursor that would lead, over vast stretches of time, to the evolution of vastly more complex and highly specialized organisms. This profound transition was facilitated by the gradual development of sophisticated communication and cooperation mechanisms between individual cells, allowing them to form organized tissues and eventually highly specialized organs with distinct and coordinated functions. It was a journey from simplicity to breathtaking complexity, a testament to life's inherent drive to innovate and adapt. Now, as we continue our journey through Earth's epic history, we arrive at one of the most astonishing and dramatic chapters in the story of life: the Cambrian explosion. This extraordinary event, which occurred approximately 541 million years ago, represents one of the most significant and, in many ways, still enigmatic periods in the entire history of life on our planet. This relatively brief, yet profoundly impactful, geological period, which extended until about 485 million years ago, marked an era of absolutely unprecedented biological diversification. It was particularly pronounced in the world's oceans, where life, seemingly from nowhere, exploded into a multitude of complex, varied, and often bizarre forms. Before the astonishing onset of the Cambrian explosion, life on Earth, while certainly present and evolving, was predominantly dominated by relatively simple microorganisms and some primitive, soft-bodied multicellular forms, often enigmatic and difficult to classify. The fossil record from this Precambrian era showcases a world of microbial mats and simple, often radially symmetrical organisms. However, during the Cambrian period itself, the geological and fossil records reveal a truly dramatic and sudden increase in both the complexity and the sheer diversity of organisms. Suddenly, in what amounts to a geological blink of an eye, almost all the major animal phyla, the fundamental body plans and groups of animals that we recognize today, appeared, alongside an impressive and bewildering variety of life forms that do not neatly fit into any modern classification, representing fascinating evolutionary experiments. One of the most striking and notable features of the Cambrian explosion was the sudden appearance and widespread development of organisms possessing hard parts. These included protective shells, rigid exoskeletons, and internal skeletons. This evolutionary innovation was a game changer for several reasons. Firstly, these hard parts provided the animals with significantly greater protection from the newly emerging predators, fostering a rapid evolutionary arms race. Secondly, and critically for our understanding today, these hard parts greatly improved the ability of these organisms to fossilize. This enhanced fossilization potential allowed scientists to gain a much clearer, more detailed view of this dynamic era through the rich fossil record, providing an invaluable window into this period of rapid diversification. Several compelling theories have been proposed to explain the seemingly sudden onset and incredible intensity of the Cambrian explosion. One prominent theory points to significant changes in atmospheric and marine oxygen levels. The Great Oxidation Event, having enriched the atmosphere and oceans with oxygen over billions of years, finally reached levels sufficient to support larger, more metabolically demanding, and more active animal life. Another theory suggests that the breakup of the supercontinent Pannotia, which occurred around this time, may have dramatically increased the number and diversity of shallow coastal habitats. These nutrient-rich, dynamic environments would have provided ideal conditions for rapid speciation and ecological diversification. A third, highly influential theory focuses on the evolution of predation. The emergence of active predators, equipped with senses and structures for hunting, would have immediately led to an intense evolutionary arms race between predators and their prey. This constant pressure to survive, to evade, and to capture would have driven rapid morphological and behavioral adaptations, accelerating the pace of evolution dramatically. Furthermore, scientists also consider the evolution of more sophisticated developmental mechanisms. Advances in gene regulation, for instance, which control how an organism's body plan develops from a single cell, and the evolution of body segmentation, allowing for specialized body regions, may have unlocked an entirely new potential for greater morphological diversity and complexity. These internal genetic innovations provided the raw material for the rapid construction of new forms. The Cambrian explosion is remarkable not only for the astonishing emergence of entirely new types of organisms, with their novel body plans and specialized adaptations, but also for the rapid development of truly complex ecosystems. During this dynamic period, the very first intricate food webs were established in the oceans. No longer was life a simple matter of microbes consuming chemicals. Now, there was a clear and profound differentiation between producers, organisms like algae that created their own food, primary consumers, herbivores that grazed on these producers, and fearsome predators, at the apex of these burgeoning food chains. This rapid increase in ecological complexity, with its intricate network of interactions and dependencies, laid the fundamental groundwork for the future evolution of all marine and eventually terrestrial ecosystems. It was the birth of a truly interconnected, interdependent biological world. Now, as the teeming oceans of the Cambrian period pulse with a vibrant, newly complex array of life, we set our sights on an even grander evolutionary leap: the conquest of the Earth. The colonization of the landmasses by life is, without exaggeration, one of the most momentous and transformative chapters in the entire history of our planet. This monumental step, which tentatively began approximately 500 million years ago, gradually yet irrevocably transformed a world that had, for billions of years, been utterly dominated by its vast, life-filled oceans into a planet teeming with the vibrant, diverse tapestry of terrestrial life we observe today. The transition of life from the boundless, liquid realms of the seas to the harsh, exposed environment of the land was not a singular, instantaneous event. Rather, it was a protracted, gradual, and incredibly complex process. It involved countless generations of organisms, both plants and animals, developing an astonishing array of physiological, structural, and reproductive adaptations to overcome the myriad challenges presented by a life lived outside of water. The journey was fraught with difficulties, demanding fundamental changes to every aspect of an organism's existence. Plants, in their silent, persistent way, were undoubtedly the pioneers in this monumental movement towards the land. They were the trailblazers, the first to bravely venture beyond the protective embrace of the waves, laying the essential foundation, literally and figuratively, for the later colonization by fauna. The very first terrestrial colonizers were likely simple life forms, perhaps similar to modern green algae, which initially inhabited the intertidal zones. These dynamic environments, situated at the boundary between land and sea, subjected these primitive organisms to regular, cyclical periods of exposure to air, sunlight, and desiccation during low tide, and then inundation during high tide. These fluctuating conditions acted as a powerful selective pressure, favoring any adaptations that allowed them to survive outside of a constantly submerged state. To thrive on dry land, these primitive organisms had to develop a suite of ingenious strategies to overcome entirely new environmental challenges. The constant threat of desiccation, or drying out, was paramount. To combat this, one of the key adaptations that evolved was the formation of a waxy cuticle. This thin, protective layer on the outer surface of plant tissues acted as a waterproof barrier, minimizing precious water loss to the atmosphere. For gas exchange, a necessity for photosynthesis, they developed specialized pores called stomata, which could open and close to regulate the intake of carbon dioxide and the release of oxygen and water vapor. Furthermore, to anchor themselves and absorb vital water and nutrients from the soil, which was a completely new substrate compared to seawater, sophisticated root systems began to evolve. Perhaps even more profoundly, the evolution of vascular tissues marked a truly revolutionary step. These internal transport systems, comprising xylem and phloem, allowed for the efficient movement of water and dissolved nutrients from the roots upwards to the aerial parts of the plant, and the transport of sugars produced during photosynthesis from the leaves to other parts. This internal plumbing system was absolutely crucial. It allowed plants to grow much taller, enabling them to compete more effectively for sunlight, and to colonize entirely new, previously inaccessible habitats further inland, away from the immediate proximity of water sources. The diversification and proliferation of land plants had an absolutely profound and transformative impact on Earth's environment, fundamentally reshaping the face of the planet. Through their widespread photosynthesis, terrestrial plants began to pump enormous quantities of oxygen into the atmosphere, further enriching the air and deepening the oxygen levels that had begun with cyanobacteria. This atmospheric shift was crucial for the evolution of larger, more active animals with higher metabolic rates. Simultaneously, the intricate root systems of plants began their silent, relentless work of breaking down solid rocks into finer particles, contributing to the formation of soil. This process fundamentally altered the geology and chemistry of Earth's surface, creating new substrates and nutrient cycles. This newly sculpted landscape, with its rich soils and oxygen-laden air, provided an unprecedented array of ecological niches for other organisms, effectively setting the grand stage for the eventual arrival and diversification of terrestrial fauna. Following in the pioneering footsteps of the plants, the first animals to make the arduous transition to land were likely arthropods. These ancient invertebrates, including creatures similar to modern millipedes, centipedes, and arachnids, spiders, and scorpions, already possessed a number of pre-adaptations that made their move to dry land somewhat less challenging than for other groups. Their sturdy exoskeletons, for instance, provided a degree of protection against desiccation, acting as an external, relatively waterproof shell. Furthermore, many arthropods already possessed respiratory systems, such as book lungs or tracheae, that were capable of exchanging gases directly with the air, a vast improvement over the gills required for aquatic respiration. The burgeoning presence of terrestrial plants offered these pioneering animals new and abundant sources of food, along with shelter and entirely new habitats, providing a powerful incentive and opportunity for the colonization of the land. The transition of vertebrates, animals with backbones, to dry land represented yet another monumental and complex milestone in this evolutionary journey. Tetrapods, the four-limbed vertebrates, are believed to have evolved from a lineage of lobe-finned fish that inhabited freshwater environments, perhaps in shallow, oxygen-poor swamps. These remarkable creatures developed a series of crucial adaptations that enabled their eventual life on land. Lungs, capable of extracting oxygen from the air, evolved from modified swim bladders. Robust, muscular limbs, homologous to the fins of their fish ancestors, developed to support their body weight against gravity and propel them across solid ground. Perhaps one of the most significant innovations was the evolution of the amniotic egg. This self-contained private pond, with its protective membranes and shell, allowed embryos to develop entirely outside of water, freeing vertebrates from the necessity of returning to aquatic environments for reproduction. The successful arrival and subsequent diversification of tetrapods on land opened an entirely new era of evolutionary possibilities. From these early amphibians, a wide variety of life forms eventually arose, populating every conceivable terrestrial niche. This lineage gave rise to the primitive reptiles, with their scaly, desiccation-resistant skin, and eventually, over vast stretches of time, to the incredible diversity of modern mammals and birds. The co-evolution of plants and animals on land simultaneously influenced the development of increasingly complex terrestrial ecosystems. Vast forests arose, supporting intricate food webs. Deserts with their specialized flora and fauna took shape. Expansive grasslands emerged, each with its own unique and dynamic network of interactions between producers, plants, various levels of consumers, herbivores and carnivores, and essential decomposers, fungi and bacteria. The land had truly become a vibrant, living canvas. And so, our chronicle brings us to an era of unparalleled grandeur and scale, the age of dinosaurs. This magnificent period, formerly known as the Mesozoic era, extended for an astonishing stretch of time from approximately 252 million years ago to a dramatic end around 66 million years ago. It is further divided into three distinct geological periods: the Triassic, the Jurassic, and the Cretaceous. This immense chapter in Earth's history was unequivocally marked by the spectacular emergence, the undisputed domination, and the eventual, dramatic extinction of the dinosaurs. These truly iconic creatures, the unchallenged protagonists of this vast expanse of geological time. The stage for the age of dinosaurs was not set without precedent. It was prepared, quite dramatically, by one of the most catastrophic events in Earth's history. The Permian Triassic extinction event, often referred to as the Great Dying, which occurred at the very end of the Permian period. This unparalleled mass extinction wiped out approximately 96% of all marine species and a staggering 70% of terrestrial vertebrate species. This cataclysmic event, possibly triggered by massive volcanic eruptions in Siberia, left an enormous number of ecological niches vacant and open across the globe. This widespread ecological vacuum, this clean slate, inadvertently set the perfect stage for the age of the dinosaurs, allowing new groups of organisms to rapidly diversify and fill the void. During the late Triassic period, roughly 230 million years ago, the very first dinosaurs made their appearance. These early representatives were generally much smaller and typically bipedal, meaning they walked on two legs. However, even these primitive forms already displayed distinctive anatomical features, particularly in their hip structure, which would become a defining characteristic for all subsequent dinosaur lineages. This unique hip anatomy allowed for an upright posture, which was a significant evolutionary advantage for locomotion. As the Triassic period gradually gave way to the Jurassic, dinosaurs began their remarkable diversification, expanding into an astonishing array of shapes, sizes, and ecological roles. They exploited the various newly available ecological niches, rapidly evolving to fill every corner of the terrestrial world. The Jurassic and Cretaceous periods truly witnessed the zenith, the golden age of dinosaur dominance. This was the era of the giants, with the emergence of colossal herbivores like the long-necked Brachiosaurus and Diplodocus, creatures of such immense scale that they reshaped landscapes with their prodigious appetites. Alongside them roamed fearsome predators, such as the powerful Allosaurus of the Jurassic, and later, the iconic apex predator of the late Cretaceous, Tyrannosaurus rex. But dinosaurs were not confined solely to the land. Their evolutionary radiation was far broader. They also conquered the skies, with specialized flying reptiles known as pterosaurs, and colonized the seas with marine reptiles like ichthyosaurs and plesiosaurs, each group developing a wide range of adaptations to thrive in their respective environments. Dinosaurs developed an incredible diversity of adaptations to survive and flourish in the varied and often challenging environments of the Mesozoic. Some, like the heavily armored Stegosaurus, evolved elaborate defensive plates along their backs and sharp, dangerous spines on their tails, offering protection against predators. Others, such as the magnificent Triceratops, developed formidable horns and elaborate bony frills, likely used for defense against rivals, display during mating rituals, or both. The astonishing diversity of the dinosaurs was also vividly reflected in their diets. There were enormous herbivores, grazing on the abundant plant life of the era, and agile carnivores, hunting across the vast plains and through the dense forests. The age of dinosaurs was not solely a story of these magnificent reptiles. It also witnessed profound and significant changes in the flora and the geography of the Earth. The continents, driven by the relentless forces of plate tectonics, were in constant motion, slowly but surely drifting, colliding, and reshaping the global landmasses. This continental drift created new geographical barriers, isolating populations and driving speciation, and also formed new land bridges, facilitating the migration and intermingling of life forms across vast distances. Botanically, the Cretaceous period saw a particularly significant evolutionary event, the first appearance of flowering plants, or angiosperms. This revolutionary plant group, with their intricate flowers and enclosed seeds, rapidly diversified and revolutionized terrestrial ecosystems, providing entirely new and highly nutritious food sources for dinosaurs and many other animals, fundamentally altering the co-evolutionary landscape. However, as all eras must, the glorious reign of the dinosaurs came to an abrupt and catastrophic end approximately 66 million years ago, at the close of the Cretaceous period, This was a mass extinction event of immense magnitude, triggered by a cataclysmic global disaster. The most widely accepted and powerfully supported theory involves the impact of a truly colossal asteroid. This immense space rock, estimated to be many kilometers in diameter, slammed into Earth in what is now the Yucatan Peninsula, Mexico, creating the immense Chicxulub crater, a scar still visible today. This asteroid impact would have unleashed an unimaginable amount of energy, equivalent to millions of nuclear bombs. The immediate aftermath would have been devastating: massive wildfires ignited by the intense heat, colossal tsunamis sweeping across coastlines, and, crucially, an immense amount of dust and debris ejected high into the atmosphere. This atmospheric veil of dust and soot would have blocked out the sun's light for months, or even years, triggering a global impact winter. This dramatic reduction in solar radiation would have drastically altered the global climate and utterly disrupted ecosystems worldwide. Photosynthesis, the base of most food webs, would have largely ceased, leading to a catastrophic collapse of food chains. The extinction of the dinosaurs was not an instantaneous event, nor was it uniform across all species. However, the drastic and rapid change in the global environment, coupled with secondary effects such as widespread ocean acidification from atmospheric carbon and global wildfires, ultimately led to the disappearance of the vast majority of dinosaur species. Yet, it's a crucial detail that not all dinosaur lineages became extinct. From the ashes of the age of dinosaurs, a resilient and adaptable group of theropod dinosaurs, small, feathered carnivores, survived and, indeed, thrived in the new world that emerged after the extinction. These survivors were the ancestors of modern birds, a living legacy of the dinosaur age, soaring through our skies today. And so, with the dramatic curtain call for the dinosaurs, our chronicle moves into a new, equally fascinating era: the rise of the mammals. The end of the age of dinosaurs, marked by that cataclysmic asteroid impact, signaled not an ending for life, but rather the beginning of a profoundly new and dynamic era in Earth's history. Before the sudden, dramatic extinction of the non-avian dinosaurs, mammals certainly existed, but they were largely relegated to the shadows. They were typically small creatures, often no larger than a modern rodent, and predominantly nocturnal. They occupied specific, often marginal, ecological niches that allowed them to avoid direct competition and, more importantly, the relentless predation of the dominant dinosaurs. These early mammals were mostly insectivorous, relying on insects and other small invertebrates for sustenance. Their life in the dark, under the cloak of night, fostered the development of particular characteristics: incredibly keen hearing, an acute sense of smell, and often whiskers for tactile exploration. These sensory adaptations, finely tuned for navigating a world in darkness, would prove to be immensely advantageous even after the dinosaurs' disappearance, providing them with a distinct edge in the newly emerging ecological landscape. The catastrophic disappearance of the non-avian dinosaurs left an enormous, unprecedented ecological void across the globe. Their sudden absence triggered dramatic and widespread changes to Earth's ecosystems. This newly reset world, stripped of its former apex predators and dominant herbivores, offered a veritable plethora of ecological opportunities. Mammals, suddenly freed from the intense competition and constant predation pressure exerted by the dinosaurs, were perfectly positioned to capitalize on this ecological vacuum. They began to rapidly diversify, embarking on what scientists call an adaptive radiation to fill the vast array of newly available niches. In the millions of years that followed the KPG extinction event, mammals underwent an astonishing and accelerated period of evolution. This adaptive radiation allowed them to explore and successfully adapt to an incredibly wide range of habitats that had previously been dominated by dinosaurs. From the dense, towering forests to the parched, expansive deserts. From the icy peaks of high mountains to the sun-drenched coastal plains, and even into the deep, enigmatic oceans, mammals evolved into an astonishing variety of shapes and sizes. They developed specialized features and behaviors to take advantage of the diverse resources available in these newly opened environments, colonizing virtually every corner of the planet. Mammals developed a suite of key evolutionary adaptations that were absolutely fundamental to their remarkable expansion and enduring success. One of the most significant was endothermy, often referred to as warm-bloodedness. This physiological capacity allowed mammals to maintain a constant, internal body temperature largely independent of external environmental fluctuations. This gave them a crucial advantage: the ability to remain active and forage in a much wider range of environmental conditions, including colder climates and during the cooler parts of the day or night, when reptiles, being ectothermic, would be sluggish. The evolution of a more complex and insulating hair or fur coat further aided in thermoregulation, providing vital protection against heat loss. Furthermore, the development of mammary glands and the practice of breastfeeding allowed for extended parental care and nourishment of offspring, significantly increasing the survival rates of their young. Additionally, the evolution of a more complex brain structure, with a larger neocortex, led to profound improvements in learning capabilities, memory retention, and sophisticated social behaviors, all contributing to their adaptive success. This era witnessed the spectacular emergence of the major groups of modern mammals that we recognize today. These include the monotremes, egg-laying mammals like the platypus, the marsupials, whose young complete their development in an external pouch, and most significantly, the placentals. Placental mammals became the most diverse and geographically widespread group, dominating most terrestrial ecosystems. Placental mammals, in particular, developed a highly successful reproductive strategy where the embryo develops internally within the mother's uterus, connected to a specialized organ called the placenta. The placenta facilitates the efficient exchange of nutrients, oxygen, and waste products between the mother and the developing fetus. This adaptation allowed for significantly longer gestation periods and the birth of more developed, viable, and often more independent offspring, greatly enhancing their chances of survival. One of the most profoundly significant developments in the vast tapestry of mammalian history was the evolution of primates, a lineage that would eventually lead, through a long and intricate series of evolutionary steps, to the rise of humans. The earliest primates were typically small, arboreal creatures, meaning they lived in trees. They possessed a set of distinctive features that were highly advantageous for a life in the forest canopy, such as flexible hands and feet with opposable thumbs or big toes, perfectly adapted for grasping branches. They also developed enhanced stereoscopic vision, with forward-facing eyes providing excellent depth perception, crucial for navigating complex three-dimensional environments and judging distances accurately. These adaptations, honed over millions of years, allowed them to move with agility and precision through their arboreal habitats. Throughout the immense expanse of the Cenozoic era, often called the Age of Mammals, these diverse creatures continued to evolve and diversify in dynamic response to a constantly changing planet. Climatic shifts, such as periods of global warming and cooling, and profound geological changes, including the formation of majestic mountain ranges, the opening and closing of vast land and sea corridors, and significant fluctuations in global temperatures and precipitation patterns, all played a critical role. These environmental transformations influenced the distribution, migration, and subsequent evolution of mammalian species, acting as powerful selective pressures. Through a continuous series of evolutionary innovations, driven by environmental change and ecological opportunity, mammals successfully managed to colonize virtually every conceivable corner of the Earth, shaping ecosystems and creating the incredibly complex and interconnected networks of life that so vividly characterize our planet today. Now, as we continue our long journey through Earth's history, we arrive at a period of profound climatic fluctuations that have dramatically sculpted landscapes and driven evolutionary change. The Ice Ages. Throughout the immense geological history of our planet, Earth has experienced several distinct ice ages. These are prolonged periods during which vast expanses of ice, in the form of massive glaciers and ice sheets, covered substantial areas of the continents, extending far beyond the polar regions. These episodes of widespread glaciation have not only fundamentally shaped the physical geography of the Earth, carving valleys and creating new landforms, but they have also profoundly influenced the evolution of life and the global distribution of ecosystems. The most recent of these grand ice ages, known as the Quaternary glaciation, commenced approximately 2.4 million years ago, marking the beginning of the Quaternary period, and it is technically still ongoing. This overarching ice age has not been a monolithic block of cold, but rather a dynamic period characterized by a series of alternating glacial and interglacial cycles. During the peaks of these cold periods, known as glacial maxima, enormous, kilometer-thick ice sheets expanded dramatically, covering vast portions of North America, Europe, Asia, and even parts of South America. These colossal ice masses extended far beyond the immediate vicinity of the poles, reaching down to surprisingly low mid-latitudes, transforming temperate regions into frozen wildernesses. The relentless advance and subsequent retreat of these immense glaciers during these ice ages had a truly transformative effect on Earth's surface. They acted like gigantic, slow-moving scrapers, profoundly reshaping the landscape through powerful processes of erosion and deposition. As they ground their way across the land, glaciers carved out distinctive U-shaped valleys, sculpted dramatic fjords along coastlines, and left behind characteristic accumulations of rock and sediment known as moraines, along with other unique geological formations. When these massive glaciers eventually melted, they released absolutely enormous volumes of trapped water, forming vast glacial lakes, such as the Great Lakes of North America, and carving out new, intricate river systems and waterways, fundamentally altering drainage patterns across continents. The ice ages also exerted a significant and global impact on sea level. During the peaks of the glacial maxima, immense quantities of Earth's water were locked up and stored within the vast continental ice sheets. This colossal sequestration of water led to a dramatic, global decline in sea level, sometimes by over 100 meters. This significant drop in sea level exposed vast tracts of continental shelf, creating new land bridges that connected continents that are now separated by oceans. A prime example is the Bering Bridge, which periodically emerged between Asia and North America, facilitating the crucial migration of species, including early humans and megafauna, between these two vast landmasses. The profound impact of the ice ages extended far beyond mere physical changes to the landscape. They also caused widespread and dramatic transformations in ecosystems and the overall distribution of life on Earth. The prevailing cold, dry conditions that characterized glacial periods favored the expansion of vast, treeless tundras and expansive steppes, hardy environments dominated by grasses and cold, adapted plants. Conversely, temperate forests and tropical jungles were restricted to smaller, more isolated refugia in warmer, wetter regions closer to the equator. Flora and fauna across the globe faced immense environmental pressure. Species either had to develop new evolutionary adaptations to cope with the harsh cold, migrate to more hospitable areas, or face the grim reality of extinction, leading to significant shifts in biodiversity and the composition of biological communities. Evolutionary adaptations to these challenging cold conditions led to the emergence of truly iconic Ice Age species, creatures that capture our imagination even today. These include the magnificent woolly mammoth, with its thick fur and enormous tusks, perfectly adapted for grazing in frigid grasslands, the formidable woolly rhinoceros, and the fearsome saber-toothed tiger, a powerful predator of the Pleistocene megafauna. These large mammals, collectively known as megafauna, developed specialized features and behaviors to survive and thrive in the harsh, glacial environments. However, many of these majestic creatures ultimately became extinct at the end of the last major glacial period, roughly 12,000 years ago. This extinction event coincided with rapid and dramatic climate changes as the planet warmed, and, significantly, possibly with the increasing hunting pressure from a rapidly expanding human population. In addition to their immense impact on geology and biology, the Ice Ages have also profoundly influenced the evolution and development of human societies. The dramatic changes in climate and geography, particularly the formation and disappearance of land bridges and the shifting distribution of resources, directly affected the migration routes of early humans. These environmental pressures influenced where human groups could settle, what resources were available to them, and how they organized their societies. These challenges and opportunities, in turn, played a significant role in the development of early agriculture, as humans sought more stable food sources, and ultimately, in the rise of the very first civilizations shaping the trajectory of human history. Now, we shift our focus from the vast, impersonal forces of planetary geology and climate to the emergence of a species that would, perhaps more than any other, fundamentally reshape the planet. The dawn of man. More than 6 million years ago, in the sprawling, ancient landscapes of sub-Saharan Africa, a specific lineage of primates began to diverge from their ape ancestors. This divergence marked the initial steps towards the hominid family, a group of beings that would become increasingly distinct due to a singular, revolutionary characteristic: bipedalism. This adaptation to habitually walking upright on two legs was a profound departure from the quadrupedal locomotion of most other primates, and it offered a cascade of significant advantages. Bipedalism allowed early hominids to travel long distances more efficiently, especially across open savannas, freeing their hands to perform other crucial tasks. With hands no longer needed for locomotion, they could carry food, water, and even their young, increasing survival rates. Crucially, it also freed their hands for the manipulation of objects and eventually the creation and use of tools, a defining characteristic of the human lineage. The earliest hominids, such as Sahelanthropus, Avoririn, and Ev Ardipithecus, show compelling evidence of partial bipedalism. While they still retained many primitive characteristics, such as adaptations for climbing trees, and likely spent a significant amount of time in arboreal environments, these pioneering beings marked the very first, tentative steps towards the fully upright, completely bipedal locomotion that would eventually characterize all later hominids, a profound shift in posture and lifestyle. As we move forward through the immense stretches of geological time, we encounter the genus Australopithecus, a group of hominids that flourished between approximately 4 and 2 million years ago. This genus includes several well-known species, such as Australopithecus afarensis, famously represented by the remarkably complete fossil skeleton known as Lucy. These Australopithecines exhibited a significantly greater adaptation to bipedalism than their earlier ancestors, with skeletal features clearly indicating habitual, upright walking. They also displayed a fascinating mosaic of both archaic, ape-like characteristics and more advanced, human-like traits. Crucially, despite their relatively small brains, which were still comparable in size to those of modern chimpanzees, Australopithecines demonstrated a truly momentous milestone in human evolution, the earliest. Rudimentary use of simple stone tools. These were not finely crafted implements, but rather naturally occurring stones or crudely flaked rocks, used for purposes like butchering carcasses or cracking open nuts. The real evolutionary watershed, a pivotal moment in the trajectory towards modern humanity, came with the appearance of the genus Homo, approximately 2.5 million years ago. A Homo habilis, often considered one of the earliest undisputed members of our own genus, displayed a significant and noticeable increase in brain size compared to the Australopithecines. More importantly, Homo habilis exhibited demonstrably more advanced tool-making skills. This development marked a crucial turning point, as the systematic use and intentional creation of tools became an increasingly integral and defining part of human survival, adaptation, and interaction with their environment. The ability to shape raw materials to extend their physical capabilities was a cognitive leap of immense significance. Evolution continued its relentless march with the emergence of Homo erectus, a truly revolutionary species that appeared around 1.9 million years ago. Homo erectus was remarkable not only for its more modern physical constitution, including longer legs and a more upright gait, which allowed it to run long distances efficiently, but also, and perhaps even more significantly, for its groundbreaking ability to control fire. The mastery of fire was a transformative technological innovation. It provided warmth, offering protection against predators, and crucially, it allowed for the cooking of food. Cooked food is easier to digest, increasing nutrient absorption and providing more energy, which is believed to have played a critical role in fueling the continued expansion of the hominid brain. Fire also fostered social cohesion, bringing groups together around a hearth. The control of fire, coupled with significant improvements in the sophistication of stone tools, such as the bifacial hand axe, represented truly monumental advances in early human technology. These innovations profoundly shaped the lifestyle and adaptive strategies of our Homo erectus. This species also marked another incredibly important milestone. Homo erectus was the first hominid to migrate out of Africa, venturing beyond the continent of its origin and spreading across vast regions of Asia and Europe. This geographic dispersion laid the essential foundation for the subsequent, diverse evolution of future Homo species in different parts of the world, leading to regional adaptations and distinct evolutionary pathways. In the colder, more challenging environments of Europe, a distinct lineage evolved, giving rise to Homo neanderthalensis, or Neanderthals. These robust, powerfully built hominids adapted specifically to the harsh, cold glacial climates of Ice Age Europe, developing specialized features and behaviors for survival in those conditions. Meanwhile, back in Africa, the evolutionary lineage that would eventually lead to Homo sapiens, our own species, began to take its distinct shape. Homo sapiens, who first appeared in Africa approximately 300,000 years ago, are distinguished by an even larger and more complex brain, particularly the frontal lobes associated with higher-order thinking. We possess an advanced capacity for abstract language, allowing for complex communication and the transmission of knowledge across generations. Our species is also characterized by sophisticated symbolic thinking, the ability to create and understand symbols, and the creation of highly complex tools and intricate art. The emergence of Homo sapiens marked the beginning of a truly new era in human evolution, one defined not just by biological adaptation, but by an unprecedented capacity for culture, innovation, and self-expression. This period saw the development of complex social structures, spiritual beliefs, and eventually, the almost complete domination of the planet by a single species. The subsequent development of agriculture, the invention of writing, and the rise of vast civilizations are all profound testaments to our species, remarkable and enduring capacity to innovate, adapt, and transform the world around us. And now, our chronicle brings us to a period of profound societal transformation, a shift so fundamental it reshaped human existence: the agricultural revolution. This pivotal period, which tentatively began about 10,000 years ago, represents a truly radical departure from previous human ways of life. It witnessed the momentous transition from nomadic hunter-gatherer societies, constantly on the move in search of sustenance, to sedentary, settled communities. These new societies were primarily focused on the systematic cultivation of plants and the organized raising of livestock. This fundamental change in how humans acquired food not only irrevocably transformed the social and economic structures of human societies, creating new hierarchies and divisions of labor, but it also had an immediate and profound impact on the planet's natural landscape, initiating a long process of human modification of the environment. Before the widespread adoption of agriculture, human populations across the globe were entirely dependent on hunting wild animals, fishing in rivers and seas, and gathering wild, edible plants. This subsistence strategy inherently limited the size of human populations, as resources in any given area were finite and often seasonal. It also necessitated a constant, often arduous, movement in search of new food sources, preventing the establishment of permanent settlements. However, the end of the last Great Ice Age brought about significant and favorable climatic changes. As the planet warmed and ice sheets retreated, certain regions of the world became far more conducive to the growth of specific wild grasses and the domestication of animals, laying the groundwork for agriculture. The development of agriculture was not a singular event that spread from one point. Instead, it began independently and more or less simultaneously in several distinct parts of the world, a testament to human ingenuity and adaptability under similar environmental pressures. Key centers of agricultural innovation included the Fertile Crescent in the Middle East, with its abundance of wild grains, the Yangtze River Valley in China, where rice cultivation first took hold, Mesoamerica, the birthplace of maize as corn, and the high plains of the Andes, where potatoes and other tubers were first domesticated. In these incredibly fertile areas, often characterized by rich soils and reliable water sources, humans began the painstaking process of domesticating plants and animals. This involved a process of selective breeding, consciously or unconsciously choosing species for desirable traits such as higher yield, easier cultivation or breeding, and superior nutritional value. The domestication of foundational crops such as wheat, corn, rice, and barley, alongside the selective breeding of animals like cattle, sheep, goats, and pigs, provided human communities with a significantly more reliable and far more abundant food source than hunting and gathering. This agricultural surplus was revolutionary. It allowed human populations to grow dramatically, leading to higher population densities, and critically, it enabled the establishment of permanent communities. These settlements, initially simple villages, gradually grew in size and complexity, giving rise, over time, to the very first cities, marking a fundamental shift in human habitation patterns. Agriculture also led directly to the specialization of labor. In hunter-gatherer societies, almost everyone was involved in the direct acquisition of food. But as agricultural societies grew in size and became more efficient at food production, not all individuals needed to engage directly in farming or animal husbandry. This surplus of labor allowed for the emergence of different roles and trades. Artisans could specialize in crafting tools or pottery, merchants could trade goods, and leaders could emerge to organize and govern these increasingly complex communities. This specialization, in turn, fueled the development of more advanced technologies, from sophisticated agricultural tools like plows and hoes, to elaborate irrigation systems designed to manage water resources more effectively. With the advent of sedentarization, the act of settling in one place, came the first clear signs of complex social and political structures. The need to manage shared water resources for irrigation, to distribute surplus food equitably, or sometimes unequitably, and to defend valuable agricultural lands from rivals or raiders, all necessitated more organized forms of governance. This led to the development of early government institutions, the establishment of laws, and the emergence of social stratification, with distinct classes and hierarchies. This period also witnessed another monumental invention, the birth of writing. Initially, writing systems emerged primarily as a practical means of recording economic transactions, keeping track of harvests, managing inventories, and documenting tribute paid to authorities. Over time, it expanded to encompass laws, histories, and literature, forever changing the way human knowledge was stored and transmitted. However, the agricultural revolution, for all its undeniable benefits and transformative power, was not without its challenges and significant negative consequences. The increasing reliance on a limited number of domesticated crops, often grown as monocultures single crops over large areas, led to problems of malnutrition as diets became less diverse. It also dramatically increased vulnerability to environmental calamities such as drought, as well as to widespread crop pests and plant diseases, which could decimate entire harvests. The close coexistence of humans with large numbers of domestic animals, along with higher population densities in agricultural settlements, tragically facilitated the transmission of zoonotic diseases, illnesses that jump from animals to humans, leading to new public health challenges. Additionally, the expansion of agriculture had a profound and often detrimental impact on the environment. Vast tracts of forests and other natural ecosystems were cleared, often through burning, to make way for agricultural fields. This widespread deforestation led to significant habitat loss for countless species, increased soil erosion as the protective canopy was removed, and altered local and regional hydrological cycles, impacting rainfall and water availability. The human footprint on the planet, once relatively light and ephemeral, became increasingly deep and permanent, setting a precedent for environmental alteration that continues to this day. Now, as human societies grew in complexity and scale, we embark upon a new chapter: empires and civilizations. Throughout the vast, unfolding tapestry of human history, countless civilizations and empires have arisen, flourished with breathtaking ingenuity, and eventually, inevitably, declined, leaving behind enduring legacies that have profoundly shaped the course of humanity. These great civilizations were not merely centers of political power or economic might, they were crucibles of innovation, advancing areas such as governance, economics, art, science, and philosophy. But crucially, they also exerted a significant and often transformative influence on the natural world and the very environments they inhabited. From the fertile, ancient river valleys that cradled the first urban centers to the sprawling, multi-continental empires of later eras, each civilization developed its own unique and intricate relationship with the environment. They harnessed natural resources, often on an unprecedented scale, and actively modified landscapes to suit their ever-growing needs, ambitions, and expanding populations. This dynamic interaction between human societies and the natural world has consistently yielded both immense benefits in terms of human progress and well-being, and significant costs, often in the form of environmental degradation and resource depletion, for both human societies and the ecosystems they depended upon. The very first civilizations, those foundational cradles of human organized society, arose in regions where agricultural productivity was exceptionally high and reliable. These included Mesopotamia, nestled between the Tigris and Euphrates rivers, ancient Egypt, flourishing along the life, giving Nile, the mysterious Indus Valley civilization in South Asia, and ancient China developing along the Yellow River. These societies were characterized by the groundbreaking development of advanced irrigation systems, elaborate networks of canals and ditches that allowed for intensive, large-scale agriculture, which in turn supported burgeoning population growth and urban centers. However, these very practices, while enabling incredible societal advancements, also led to unforeseen environmental consequences, such as the gradual salinization of soils due to irrigation in arid climates, widespread deforestation for timber and fuel, and significant alteration of delicate river ecosystems. In the New World, civilizations in Mesoamerica, such as the Mayans, and in the Andes, like the Incas, developed highly ingenious agricultural techniques specifically adapted to their unique and often challenging environments. The Mayans, for example, utilized sophisticated, milpar systems of rotational farming and raised fields, while the Incas mastered terrace farming, carving vast, productive agricultural steppes into steep mountain slopes. While these innovative practices allowed for the development of complex, highly organized societies in challenging topographical and climatic conditions, they also involved a massive and deliberate transformation of local landscapes, reshaping mountains and forests to sustain their populations. The expansion of vast empires, such as the Roman Empire with its sprawling network of roads and cities, the mighty Persian Empire, the nomadic Mongol Empire, and the successive imperial dynasties of China, had an even more profound and far-reaching impact on the environment. The monumental construction of cities, intricate road networks, and colossal aqueducts required immense quantities of raw materials. The systematic exploitation of natural resources, timber for building and fuel, metals for tools and weapons, stone for monumental structures, occurred on an industrial scale. Furthermore, these empires often introduced exotic species of plants and animals into new environments, sometimes intentionally for agriculture, sometimes accidentally, leading to unforeseen ecological disruptions. Deforestation, driven by the insatiable demands for agriculture, construction materials, and fuel, was a common practice across many empires, leading to widespread soil erosion, loss of biodiversity, and altered hydrological cycles across vast regions. The period of great European exploration and subsequent colonialism, beginning in the 15th century, represented yet another profound and globally impactful phase in the complex interaction between human civilizations and the natural environment. The relentless search for new trade routes to distant, resource-rich lands, coupled with an insatiable demand for exotic spices and precious metals, fueled these ambitious voyages. This era led directly to what is known as the Columbian Exchange, an unprecedented and truly massive transfer of plants, animals, foods, human populations, technologies, and sadly, diseases, between the Old World Europe, Asia, Africa, and the New World, the Americas. While certain aspects of this exchange were undeniably beneficial, such as the introduction of highly nutritious crops like corn and potatoes to Europe, which significantly boosted population growth, other consequences were devastating. For the indigenous populations of the Americas, in particular, the arrival of Europeans brought with it a host of previously unknown diseases, such as smallpox, measles, and influenza, against which they had no natural immunity. This biological onslaught led to drastic declines in indigenous populations, often by 90% or more, fundamentally altering the demographic and social landscape of entire continents. Furthermore, the systematic exploitation of resources in newly discovered lands and the imposition of brutal colonial systems radically transformed local ecosystems and societies, often to serve the economic interests of distant European powers. The immense European demand for sugar, for instance, led to the establishment of vast, labor-intensive plantations in the Caribbean, Brazil, and other parts of the Americas. These plantations were primarily worked by enslaved African people, forcibly transported across the Atlantic, initiating the tragic and extensive history of the transatlantic slave trade, a dark chapter in human history with profound environmental and social costs. Moreover, the Age of Exploration laid the foundational blueprints for the modern world system. This system is characterized by its deep global interconnections, its intricate web of trade routes, and unfortunately, its inherent economic inequalities that persist to this day. The establishment of these global trade routes and the massive accumulation of wealth, particularly in European mercantile centers, directly facilitated the nascent rise of capitalism as a dominant economic system and spurred the development of powerful national economies and vast maritime empires, forever altering the geopolitical landscape. The cultural influence of the Age of Exploration was also immense and complex. Exposure to a myriad of diverse cultures, often through coercive means, led to a forced mixture of traditions, languages, and beliefs. While this created a rich tapestry of cultural exchange in some instances, it often occurred within contexts of domination, oppression, and fierce resistance. European expansion also ignited fervent philosophical and ethical debates back in Europe, prompting deep questions about the morality of conquest, the treatment of indigenous populations, and the very nature of human rights. These early debates, though often self-serving, contributed to the slow, evolving development of thought on universal human rights and the concept of national sovereignty, ideas that would gain prominence centuries later. And so, we arrive at a chapter that fundamentally reshaped human existence, accelerating change at an unprecedented pace: the Industrial Revolution, beginning in Britain during the latter half of the 18th century, and subsequently spreading its transformative influence throughout the world during the 19th and 20th centuries. This period marked a truly radical and irreversible transformation in the way humans produced goods, organized themselves socially, and, perhaps most significantly, interacted with and impacted the natural environment. This era of unparalleled technological innovation and rapid change not only catalyzed astounding economic growth and profoundly altered social structures, creating new classes and urban centers, but it also initiated an environmental impact of such immense scale that its repercussions continue to resonate across the globe today. The very genesis of the Industrial Revolution is often attributed to a series of groundbreaking mechanical innovations, chief among them being the significant improvements to the steam engine by James Watt in the late 1700s. This revolutionary invention, building upon earlier, less efficient designs, fundamentally changed the energy landscape. It allowed for the widespread use of coal as the primary, abundant energy source, effectively replacing the previous, more limited reliance on renewable energy sources such as water power from mills and wood. The steam engine, with its reliable and concentrated power, ushered in a new era of factory machinery, dramatically improving efficiency and scale in the production of textiles, iron, and a vast array of other manufactured goods, setting the stage for mass production. The widespread introduction of machinery into every aspect of production, from spinning cotton to forging metal, led to an exponential increase in demand for raw materials. This insatiable appetite for resources like coal and iron ore stimulated a massive expansion of mining and metallurgy industries. These industries, operating on an unprecedented scale, literally transformed entire landscapes. Coal mines burrowed deep into the earth, extracting fossilized energy, while vast tracts of forests were cleared to provide charcoal for the hungry blast furnaces of iron smelters. This large-scale resource extraction and land modification profoundly altered local ecosystems, disrupted natural drainage patterns, and left lasting scars on the environment. The exponential growth of factories and the associated, rapid urbanization that accompanied them radically reshaped urban environments across industrializing nations. Cities like Manchester in England and London expanded at breathtaking speeds, often without adequate infrastructure to cope with the influx of millions of people seeking work. This uncontrolled growth led to levels of air and water pollution previously unimaginable. The burning of immense quantities of coal for energy and heating generated thick, pervasive smog that choked cities, while industrial and domestic wastewater, often completely untreated, was dumped directly into rivers and streams, turning them into open sewers and contaminating vital water sources for entire populations. The Industrial Revolution also witnessed the birth and rapid development of the modern transportation system. The invention of the steam locomotive by George Stephenson revolutionized land transportation, enabling the rapid movement of raw materials, manufactured goods, and people across continents. Concurrently, significant improvements in steamship technology transformed maritime transportation, making global trade faster, more reliable, and more efficient. These immense advances in transportation greatly facilitated global trade networks and directly enabled the expansion of imperialism, as colonial powers could more easily extract resources and project power. However, these new modes of transport also contributed significantly to the emission of greenhouse gases into the atmosphere and facilitated the accidental or intentional introduction of invasive species into new environments, further disrupting delicate ecosystems worldwide. At the agricultural level, the Industrial Revolution brought forth a wave of technological innovations that profoundly increased productivity. Inventions such as the mechanical seeder, which allowed for more efficient planting, and the threshing machine, which greatly sped up grain processing, meant that far more food could be produced with less labor. However, this mechanization of agriculture, coupled with the increasing adoption of practices like monoculture, growing a single crop over large areas, had its own negative impacts. It often led to a significant reduction in biodiversity on farms and, over time, depleted soil health, contributing to widespread soil erosion and the loss of essential nutrients from the land, creating a dependency on artificial fertilizers. Now, our historical trajectory brings us to a period of unprecedented global conflict and human suffering: the World Wars. The two global conflicts of the 20th century represent some of the most devastating episodes in the entire span of human history. They are remembered not only for the immense human suffering, the staggering loss of life, and the profound psychological trauma they inflicted, but also for their far-reaching and deeply transformative impact on human society, political structures, and, critically, the natural environment. These global conflicts irrevocably transformed nations, reshaped cultures, and left deep, enduring scars on natural landscapes that, in many places, persist to this very day. The First World War, which raged from 1914 to 1918 and was tragically known as the Great War, introduced an entirely new and horrifying scale of destruction. This was primarily driven by the widespread use of modern battlefield technology. New weapons like rapid-firing machine guns, devastating heavy artillery, and insidious poison gases were deployed. For the first time, warfare extended to the air with fledgling air forces and to armored vehicles on the ground. The intense, protracted shelling and brutal trench battles, particularly on the Western Front, transformed vast areas of previously fertile countryside into desolate, moon-like landscapes. Forests were obliterated, agricultural fields became churned mud, and ecosystems were utterly destroyed. Soils and waters were contaminated with an insidious cocktail of chemicals, unexploded ordnance, and heavy metals, leaving a toxic legacy for decades. World War II, which engulfed the globe from 1939 to 1945, further expanded both the geographical scope and the sheer scale of environmental impact. This was a concept of total war, meaning that it involved not just professional armies, but entire societies, with national economies and populations fully mobilized for the war effort. This required a massive increase in industrial production, directed almost entirely towards armaments and supplies, leading to the rapid depletion of natural resources and a dramatic increase in pollution from factories. Strategic bombing raids, designed to cripple enemy industries and morale, devastated entire cities, often flattening them to rubble. These direct attacks caused immense indirect environmental damage through widespread fires, the destruction of vital infrastructure, and the massive displacement of millions of people, who then put pressure on new environments. The world wars also inadvertently accelerated the development and widespread proliferation of technologies that would go on to have lasting and profound environmental impacts, extending far beyond the immediate conflict. World War II, in particular, was a crucible for scientific and technological advancement. It led directly to the development of nuclear energy, an entirely new and immensely powerful energy source, but also brought with it the terrifying subsequent threat of widespread radioactive contamination. This threat was tragically and devastatingly illustrated by the atomic bombings of Hiroshima and Nagasaki, which forever altered humanity's relationship with warfare and its destructive potential. On a profound social level, the world wars acted as powerful catalysts, fostering immense changes in political, economic, and cultural structures across the globe. World War I dismantled ancient empires, such as the Austro-Hungarian, Ottoman, and Russian empires, and redrew political maps, especially in Europe and the Middle East. This often created new nation-states and, in many cases, laid the volatile groundwork for future conflicts and geopolitical instability. World War II, for its part, marked the decisive rise of two global superpowers, the United States and the Soviet Union, and ushered in the perilous era of the Cold War, a decades-long standoff. In an attempt to prevent future global catastrophes, it also led to the establishment of the United Nations, an international organization dedicated to fostering peace, cooperation, and collective security among nations. The sheer magnitude of the suffering and destruction wrought by the world wars also galvanized powerful movements toward human rights and social justice. These included the widespread decolonization movements that swept across Asia and Africa, as well as significant advancements in gender equality and civil rights movements in many Western nations. The profound experience of widespread death and destruction compelled a global reflection on the nature of war, the elusive pursuit of peace, and the fundamental conditions of the human condition, leading to a re-evaluation of societal values and priorities. Now, as the smoke of global conflicts begins to clear, we enter an era of rapid technological advancement and unprecedented global interconnectedness. The digital age and globalization. The profound transition to the digital age, coupled with the accelerated and pervasive process of globalization, has been the defining characteristic of the last decades of the 20th century and the initial decades of the 21st century. These twin forces have profoundly and irrevocably transformed virtually all aspects of human society, from our daily lives to the very structure of global economies and cultures. The digital revolution, a relentless wave of innovation, has been primarily driven by the continuous development of personal computing, the explosive growth of the Internet, and the ubiquity of mobile telecommunications. These technologies have fundamentally altered the way people communicate with one another, how they work, how they access information, and how they entertain themselves. The emergence of the World Wide Web in the early 1990s and its subsequent rapid expansion into nearly every corner of the globe have democratized access to information on an unprecedented scale. This has effectively eliminated many traditional geographic and cultural barriers, fostering an era of unparalleled information exchange and knowledge dissemination. Social media platforms and various digital communication tools have fundamentally transformed social interactions and methods of community organizing. They allow people to connect, share ideas, and collaborate in entirely new and often instantaneous ways, transcending physical distances. However, this digital interconnectedness has also presented significant challenges. Concerns about data privacy and the security of personal information have become paramount as vast amounts of user data are collected and stored. Furthermore, the rapid spread of misinformation and disinformation, often amplified by algorithmic biases, poses a serious threat to informed public discourse and democratic processes. Globalization, a process greatly fueled and accelerated by digital technology, has integrated the world's economies to an extent previously unimaginable. International trade and cross-border investment have expanded enormously, driven by policies of trade liberalization and immense advancements in transportation logistics and communication. The development of complex global supply chains, where components are manufactured in multiple countries and assembled elsewhere, coupled with interconnected financial markets, has created a truly global economy. In this intricate web, events in one region, whether economic or political, can have instantaneous and far-reaching impacts across the entire world, demonstrating the profound interdependency of nations. However, globalization has also contributed to growing inequalities, both within individual countries and between different nations. The concentration of immense wealth and power in the hands of a relatively small number of transnational corporations, combined with the relocation of manufacturing jobs to countries with lower labor costs, has generated intense debates about economic justice, fair labor practices, and the erosion of national sovereignty in economic decision-making. The digital age and globalization have also exerted a significant and complex impact on the environment. On one hand, information and communication technologies have paradoxically contributed to greater energy efficiency in some sectors and have facilitated the development of more sustainable solutions, such as smart grids and remote environmental monitoring systems, allowing for better management of resources. On the other hand, the ever-increasing global demand for electronic devices, with their short life cycles, has led to a dramatic increase in the extraction of rare earth minerals and other raw materials, often with significant environmental costs, and has generated a growing problem of electronic waste. Furthermore, the relentless pace of globalization has accelerated patterns of consumption and environmental degradation through the intensive exploitation of natural resources to feed global supply chains and consumer demand. In the cultural sphere, globalization and digitalization have promoted an unprecedented level of cultural exchange and, in some respects, diversity, as people are exposed to a wider array of global influences. However, this has also raised significant concerns about cultural homogenization, where dominant cultural forms, often from Western nations, overshadow and erode local identities and traditions. The global spread of pop culture, music, film, and fashion has indeed created a vibrant, interconnected global cultural mosaic, but it has also generated ongoing debates about cultural domination and the ethics of cultural appropriation, as traditional forms are sometimes commodified without proper recognition or respect. Now, our journey through human technological evolution brings us to a frontier that promises both immense progress and profound ethical challenges: the era of artificial intelligence. The dawn of the era of artificial intelligence, particularly in recent decades, has brought forth unprecedented technological advances. These innovations are already profoundly transforming industries, improving efficiencies across countless sectors, and opening entirely new frontiers in scientific research and technological development. From medical diagnostics to complex data analysis, AI is rapidly becoming an integral part of our daily lives. However, this rapid and accelerating advancement also poses a number of significant risks and complex challenges that, if not carefully and ethically managed, could potentially endanger humanity itself, or at least dramatically alter our societal structures in unforeseen ways. One of the foremost and most immediate risks associated with the widespread adoption of artificial intelligence is the potential for significant job loss and widespread economic disruption. AI-powered automation, with its increasing sophistication, has the potential to surpass human capabilities in a broad range of tasks, from routine clerical work to complex analytical roles. This could lead to mass unemployment in sectors that have traditionally relied heavily on human labor, creating immense societal upheaval. Such a dramatic shift could exacerbate existing economic and social inequalities, further concentrating wealth in the hands of those who own and control AI technologies, thereby creating new tensions and posing immense challenges for existing welfare systems and social safety nets. Another significant and deeply concerning risk is the frightening possibility of artificial intelligence being developed and deployed for malicious purposes. Advanced AI systems could be utilized in sophisticated forms of cyberwarfare, orchestrating unprecedented attacks on critical infrastructure, or in advanced espionage operations, compromising national security. Perhaps most disturbingly, AI could be integrated into the creation of highly autonomous weapon systems, increasing the lethality and effectiveness of armed conflicts to an unimaginable degree. The unregulated development and use of AI in military contexts raise profound ethical and safety concerns, as machines could potentially make life or death decisions without direct human supervision or accountability, blurring the lines of responsibility and morality in warfare. Data privacy and the security of personal information are also paramount concerns in this burgeoning age of artificial intelligence. These complex systems, particularly those employing machine learning, rely on processing and analyzing vast, often unfathomable, amounts of data to train and improve their performance. This inherent reliance on massive datasets poses significant privacy risks if personal data is collected, stored, or used inappropriately, without adequate consent or robust safeguards. Furthermore, highly advanced AI systems could empower new and pervasive forms of surveillance and social control, both by governments and powerful corporations, potentially eroding individual liberties and fostering oppressive regimes. One of the most widely discussed and philosophically unsettling risks in the field of artificial intelligence is the theoretical scenario known as the technological singularity. This concept posits a future point where artificial intelligence would not merely match, but decisively surpass human intelligence, leading to an exponential, self-accelerating growth in knowledge and technological capability that human beings could no longer control, comprehend, or even predict. This hypothetical scenario raises fundamental questions about human control, the very nature of autonomy, and indeed, the long-term survival of humanity itself, as a super-intelligent AI could pursue its goals in ways utterly alien and potentially detrimental to human interests. The crucial issue of aligning values between human beings and increasingly intelligent machines is another area of intense concern and active research. As AI systems become more and more advanced, possessing greater autonomy and decision-making capabilities, ensuring that they consistently act in accordance with human interests, ethical principles, and societal values becomes an absolutely critical challenge. AI systems with misaligned goals, even if designed with seemingly benign intentions, could, through unintended consequences or unforeseen emergent behaviors, carry out harmful or unwanted actions with unpredictable and potentially catastrophic ramifications for humanity. The concentration of power and control over advanced AI technologies in the hands of a limited number of corporations or governments also poses significant risks to democratic principles and equitable societal development. Such a concentration could lead to abuses of power, the suppression of dissent through sophisticated surveillance and manipulation, and the gradual erosion of democratic institutions and fundamental human rights. The unchecked power of AI, wielded by a few, could create unprecedented forms of societal control. Finally, a more subtle but equally important risk is the potential for humanity to lose critical skills and foundational knowledge due to an over-reliance on AI and automation. As AI systems become increasingly capable of performing complex tasks, there is a danger that humans might become less proficient in these areas, making us vulnerable in situations where technology fails, is inaccessible, or is intentionally withheld. This could lead to a dependency that undermines human agency and resilience. Now, as we contemplate the profound transformations brought by artificial intelligence, let us turn our gaze outward to a realm that has captivated humanity's imagination for millennia, the space age. The human space age, which dramatically commenced in the latter half of the 20th century with the launch of Sputnik and the first human spaceflights, has now entered a truly new and immensely exciting phase. With a rapidly growing global interest in space exploration, driven by both traditional government space agencies and an increasingly dynamic landscape of private entities and commercial enterprises, humanity is actively preparing to establish a sustained, long-term presence not only on our closest celestial neighbor, the Moon, but also on the enigmatic red planet, Mars, and eventually, far beyond, through the deployment of advanced space stations and other intricate infrastructure. The Moon, that familiar, pockmarked natural satellite that has silently orbited Earth for billions of years, has once again emerged as a key strategic objective in this burgeoning new era of space exploration. Ambitious projects, such as NASA's Artemis program, are not merely seeking to replicate the historic Apollo missions by returning humans to the lunar surface. Their overarching goal is far more expansive: to establish a sustainable human presence on and around the Moon by the late 2020s. These ambitious initiatives include meticulously detailed plans to construct the Gateway, a sophisticated space station that will orbit the Moon. This lunar, orbiting outpost will serve a multitude of critical functions. It will be a cutting-edge scientific laboratory, a comfortable habitation module for astronauts, and crucially, a strategic staging port for future missions venturing deeper into the vastness of space, acting as a cosmic way station. Mars, with its captivating geology, its tantalizing evidence of past liquid water, and its enduring potential to have hosted ancient microbial life, represents the next immense horizon for human exploration. Missions from established space agencies like NASA, alongside the incredibly ambitious projects spearheaded by pioneering private companies such as SpaceX, are unequivocally aiming to send human beings to Mars within the coming decades. Establishing a permanent human base on Mars presents a formidable array of challenges, far greater than those encountered on the Moon. These include its incredibly thin, primarily carbon dioxide atmosphere, its brutally low temperatures, the significant radiation environment, and the crucial need to generate vital resources in situ, meaning on Mars itself, such as oxygen and water. However, relentless advances in propulsion technology, life support systems, and space science are steadily bringing this once distant goal closer to a tangible reality. In addition to the Moon and Mars, orbiting space stations continue to be an absolutely crucial and indispensable component of humanity's sustained presence in space. The International Space Station, ISS, a magnificent emblem of unprecedented international cooperation in space, has provided an invaluable platform for groundbreaking scientific research and the rigorous demonstration of cutting-edge space technologies ever since its initial launch in 1998. It has been a continuous human outpost in low Earth orbit, fostering countless scientific discoveries. However, as the venerable ISS approaches the end of its useful operational life, new generations of space stations are already being meticulously planned and developed. These future stations could be operated by innovative international consortia of nations, or even entirely by private entities, vastly expanding the opportunities for commercial space research, manufacturing in microgravity, and the burgeoning industry of space tourism, opening up the cosmos to a broader segment of humanity. Exploration extends even further beyond the immediate reach of Mars, with ambitious robotic missions already on the horizon, targeting distant asteroids, the enigmatic moons of Jupiter and Saturn, such as Europa and Titan, which hold potential for subsurface oceans, and eventually venturing into the truly far reaches of our solar system and beyond. These groundbreaking missions are driven by a fundamental human desire to better understand the processes of formation and evolution of our solar system, to search for clues about the origins of life, and to investigate the profound potential for life beyond Earth, seeking answers to some of humanity's deepest questions about our place in the cosmos. And now, as we contemplate humanity's ventures into the cosmos, we must turn our attention inwards to the very future of our species, the evolution of Homo sapiens sapiens. The evolution of our own species, Homo sapiens sapiens, is a continuous, dynamic process that has unfolded over hundreds of thousands of years. It has taken us from our origins on the sun-drenched savannas of Africa, where our earliest ancestors first walked upright, to our current status as the dominant species in virtually all terrestrial ecosystems across the entire planet. Looking ahead, the future trajectory of our evolution is a subject of immense speculation and intense scientific interest, involving not only the ongoing processes of natural evolution, but also the increasingly plausible possibility of directed evolution through advanced technology. Natural evolution, the relentless engine of biological diversity on Earth, has historically been driven by a complex interplay of processes: natural selection, where advantageous traits are favored; genetic mutation, the source of new variation; gene flow, the movement of genes between populations; and genetic drift, random changes in gene frequencies. In the case of modern humans, the influence of these traditional forces of natural evolution has been profoundly altered and, in many ways, attenuated by our unparalleled capacity for technology and culture. Our remarkable abilities to modify our environment, to develop sophisticated medical treatments that overcome diseases, and to create incredibly complex social systems have significantly reduced many of the selective pressures that historically drove biological evolution in our ancestors. We have, to a large extent, created a buffer against many natural challenges. However, this does not imply that human evolution has entirely ceased. Subtle, ongoing changes continue to occur within our collective genome, reflecting adaptations to new, modern challenges. These include, for instance, the evolving resistance to certain diseases as pathogens adapt, and the ongoing ability to metabolize specific foods, such as lactose tolerance in populations that historically relied on dairy. Furthermore, the accelerating process of globalization has dramatically increased gene flow between previously isolated human populations across the world, leading to a constant mixing and redistribution of the human genetic heritage, subtly altering our species' genetic makeup over generations. Looking explicitly to the future, the possibility of directed evolution through advanced genetic engineering is emerging as an increasingly plausible and, for some, even inevitable reality. Revolutionary tools like CRISPR-Cas9, a highly precise gene editing technology, have opened the door to making targeted, specific edits to the human genome, This capability holds immense potential for correcting harmful genetic mutations that cause debilitating diseases, and potentially for enhancing specific human characteristics, such as resistance to a wider range of illnesses, extending longevity, or even improving certain cognitive abilities. However, these groundbreaking possibilities are accompanied by a torrent of profound ethical, social, and practical questions. Who would have access to these incredibly powerful genetic technologies? How would they be regulated to prevent misuse or unintended consequences? What are the risks of unforeseen side effects on the complex interplay of genes? The very possibility of designing human beings, of selecting for specific traits, could dramatically deepen existing social and economic inequalities, creating a genetic divide between those who can afford such enhancements and those who cannot. It also raises fundamental philosophical questions about the very essence of humanity, the value of natural diversity, and what it truly means to be human. Beyond the realm of direct genetic manipulation, the convergence of biology with other rapidly advancing technologies, such as artificial intelligence, robotics, and nanotechnology, suggests scenarios where human evolution could take unprecedented and truly unpredictable directions. The seamless integration of cybernetic and biological technologies could potentially lead to the emergence of augmented humans, beings whose physical and cognitive capabilities are dramatically expanded and enhanced through technological means, blurring the traditional boundaries between human and machine. This could range from advanced prosthetics, integrated directly with the nervous system, to neural implants that boost memory or processing speed, leading to a new definition of human potential and, perhaps, a new species. Now, as our grand narrative nears its conclusion, having traversed billions of years of cosmic and planetary history, we must confront a sobering, yet vital, chapter: threats to life on Earth. Despite its astonishing resilience and the incredible diversity of life forms it has fostered, life on Earth faces a spectrum of potential threats. These threats, varying wildly in their origin and scale, could trigger devastating mass extinction events, fundamentally altering the trajectory of life, or, in the most extreme scenarios, even lead to the complete end of life as we know it on this planet. Asteroid impacts, those cosmic billiard balls hurtling through space, have played a crucial and often cataclysmic role in Earth's deep history. The most famous example, of course, is the impact approximately 66 million years ago, which is widely accepted as the primary cause of the extinction of the dinosaurs. A sufficiently large asteroid, upon impacting Earth, could release an amount of energy comparable to millions of nuclear bombs, unleashing a cascade of destructive events. This could include massive wildfires ignited globally, colossal tsunamis sweeping across continents, and, most critically, the ejection of immense quantities of dust and debris high into the atmosphere. This atmospheric veil would block out sunlight for extended periods, triggering a devastating impact winter, dramatically reducing global temperatures and utterly disrupting ecosystems worldwide. Photosynthesis would largely cease, leading to a catastrophic collapse of food chains and ultimately, mass extinction across the planet. Solar flares, powerful explosions on the surface of our sun, can release enormous amounts of energy and highly charged particles into space. While Earth's robust magnetic field and its protective atmosphere generally shield us from the worst effects of these events, an exceptionally powerful solar flare, or a coronal mass ejection, CME, could potentially overwhelm these defenses. Such an event could damage the Earth's ozone layer, triggering adverse climate effects, and, more immediately, drastically disrupt the electronic and communication systems upon which our modern society is now deeply dependent, leading to widespread power outages, communication blackouts, and economic chaos. Nuclear war represents one of the most immediate, terrifying, and entirely self-inflicted threats to life on Earth. Beyond the initial, unimaginable devastation and loss of life caused by the explosions themselves, a full-scale global nuclear war could trigger a catastrophic nuclear winter. The burning of cities, forests, and industrial centers would inject immense quantities of soot and dust high into the atmosphere, creating a persistent, global shroud that would block out sunlight. This would lead to a dramatic and prolonged lowering of global temperatures, widespread crop failures, and famine on a global scale, putting the vast majority of species, including humanity, at severe risk of extinction. The long-term effects of radiation and environmental collapse would render much of the planet uninhabitable for generations. Pandemics, as has been starkly evidenced in recent times, can have devastating and far-reaching effects on human society and, by extension, on interdependent ecosystems. A highly virulent and lethal pathogen, especially one that can be transmitted easily through the air and possesses a long incubation period, could potentially decimate the human population, leading to societal collapse and immense suffering. While a pandemic is less likely to eradicate all forms of life on Earth, it could fundamentally alter human civilization, profoundly reshape the global population, and severely impact the complex ecosystems that depend on human activity. In addition to these highly impactful scenarios, there are other significant potential threats that could endanger life on Earth, albeit with varying probabilities and timescales. The eruption of a supervolcano, for instance, a rare but immensely powerful geological event, could release enough ash, aerosols, and volcanic gases into the atmosphere to block sunlight for years, leading to a volcanic winter, with catastrophic consequences for global agriculture and ecosystems. Significant, abrupt changes in Earth's orbital parameters or the tilt of its rotational axis, while extremely unlikely in the foreseeable future, could dramatically alter global climate patterns, leading to rapid and devastating environmental shifts. A super-intelligent artificial intelligence, with goals that become fundamentally misaligned with human values, could pose an existential threat, whether through manipulating global systems to achieve its own ends or by developing uncontrollable, self-replicating weapons. And while climate change is an ongoing process with gradual impacts, an abrupt, runaway, and extreme climate shift could trigger cascading extinction events by rapidly altering habitats and pushing ecosystems beyond their adaptive capacities. To mitigate these diverse and formidable threats, continuous scientific research, robust preparedness strategies, and unwavering international cooperation are absolutely crucial. Early detection systems for asteroids, stringent regulation of nuclear and biological weapons, vigilant monitoring of emerging pathogens, and the thoughtful, ethical management of artificial intelligence development are just some of the critical fields where proactive, collaborative efforts can significantly reduce the risks of catastrophic scenarios and safeguard the long-term future of life on Earth. Finally, as our grand chronicle draws to a close, we arrive at the ultimate, inescapable truth, the end of the Earth, an inevitable destiny in the cosmos. The end of Earth as a planet, its ultimate demise as a habitable world, is an event that, while situated in the unimaginably distant future, is an assured certainty. This destiny is dictated by the relentless astronomical and cosmic processes that govern the universe, particularly the life cycle of our own star, the Sun. The future life of Earth, its continued existence as a world, is intrinsically and irrevocably linked to the evolution of our Sun. Currently, our Sun resides in its stable, main sequence phase. During this phase, it diligently fuses hydrogen into helium in its core, radiating the light and heat that sustain life on Earth. This stable phase, however, is finite. Our Sun will continue this hydrogen fusion for approximately 5 billion more years, a vast span of time, but a finite one nonetheless. As the Sun gradually exhausts its primary hydrogen fuel in its core, it will begin a profound transformation. It will cease fusing hydrogen and instead begin to fuse helium, igniting a new phase of its life cycle. During this transition, the Sun will dramatically expand, swelling into a colossal, red giant star. This red giant phase will see our Sun grow to an immense size, a bloated, cooler, but vastly larger star. Its outer layers will expand outwards, almost certainly engulfing the orbits of Mercury and Venus, and quite possibly that of Earth as well. As the Sun expands and its outer layers engulf our planet, the intense radiation and dramatically rising temperatures will have a devastating effect. Earth's oceans, the cradles of life, will boil away and evaporate completely, disappearing into space as superheated steam. The planet's atmosphere will be stripped away by the intense solar winds, leaving behind a barren, scorched, and utterly lifeless rock. Even if Earth miraculously manages to avoid being directly engulfed by the Sun's expanding outer envelope, its fate as a parched, sterilized, and utterly lifeless planet is virtually certain. The sheer heat and radiation will render it completely uninhabitable. Paradoxically, during this red giant phase, the Sun will also experience significant mass loss as it sheds its outer layers into space. This reduction in the Sun's gravitational pull could, in theory, cause Earth to drift into a slightly more distant orbit. However, even if this orbital shift occurs, saving Earth from direct absorption, it would not save it from the utter destruction of its habitability. The conditions would remain far too extreme for any form of life to endure. After the dramatic red giant phase, the Sun will undergo another profound transformation. It will eject its remaining outer layers into space, forming a beautiful, ethereal, planetary nebula, a shimmering shell of gas and dust. What remains at the core will be a small, incredibly dense, and incredibly hot remnant, a white dwarf. This stellar corpse, though much smaller and far less luminous than the Sun once was, will still radiate residual heat for billions of years. Earth, if it still exists as a coherent planet, would be a dark, icy, and desolate world orbiting the cold, faint remains of its former Sun, a frozen monument to a once vibrant past. As we bring this immensely long, inspiring journey through the history and future potential of the Earth to its quiet, inevitable conclusion, we are called to a profound moment of reflection. We are, in this brief cosmic instant, the conscious stewards of this remarkable world, this vibrant blue marble teeming with life. This journey through billions of years of cosmic forces, geological upheavals, and evolutionary miracles underscores the fragility and preciousness of our unique planetary home. It compels us to consider our profound role as guardians of this world, committing ourselves, in the fleeting present, to a future in which life, in all its astonishing forms, can continue to flourish, to adapt, and to evolve, for as long as this pale blue dot remains a haven in the boundless, silent cosmos.